Thank you.
All right.
So, just a brief introduction. My name is Allison Tang, and I'm a junior at Great Valley High School.
My name is Prisha Roy, and I'm also a junior at Great Valley. And Allison and I were partners in the MIT Think Progress, and our hope is that this meeting today will help us further our progression into developing our ideal prototype.
Okay.
And with that, we have compiled a couple of questions to ask you. And if you don't know the answer or you don't want to answer, that is perfectly fine. But these questions would just like really help us with our design process because we are attempting to make a disinfectant and desalinization machine to be put in marginalized areas for the MIT Think project. And we were inspired by your Oregon State article, which is why my first question is how did you know like what equipment to pick more specifically? How did you know that the perforated plate and the reference table in your Oregon State article were the best and most efficient parts to like helping your design like run smoothly?
Okay. So, first of all, thank you very much for your introductions. I am also going to give a quick introduction for myself. My name is Deepak Sharma. I am a research faculty at Oregon State University in the School of Mechanical, Industrial, and Manufacturing Engineering. I did my PhD from Oregon State University itself, and the work you are referencing to came out of my PhD work. So, how we came up identify that these are efficient devices that we incorporated in the system, and you want to understand the decision making or the metrics of evaluation, how we selected or down selected those. Okay, so what we did initially, we wanted to design. It was our project funded by DOE and ARPA-E that we need to design a desalination system that is more energy efficient and cost effective. And for both of those there are some pieces tied to the machine itself. If you want something to be more cost effective, you want to cut down its maintenance cost and operational cost. So those were two criterias. And maintenance cost, it is all about how much fouling you are having in system and things like that. Excuse me. And for operational cost, you want to cut down the energy for that. However, when we talk about perforated plate atomizer, it was our trick to bring down the maintenance cost significantly by suppressing fouling. And so we chatted with some of the folks have been working with atomizers for like multi decades now. And when we talked with them and also went through some literature, we realized that existing atomizers, especially when we have air and liquid passing through it for the atomization process, we call them air blast atomizers. And air blast atomizer fits in our criteria as well because our desalination system required both streams, air and liquid. So then we pivoted on that, did some quick study, and we realized, whoa, they fouled very quick, like in no time, in 30 minutes or so. And we wanted to design a system that can like run for 25 years or so, the life like we were expecting to achieve that. So we wanted something that does not fall that frequently. The basic idea we started with is like if if there is not the orifice are not that complicatedly designed how they are in atomizers, those are available in the market. Then we started with we did preliminary tests with just a sheet with multiple perforations in it and passing air through it. But then we realized like okay, it might suppress fouling, but it is not going to atomize. Then we needed to make sure, and why it is not going to atomize. During those quick and dirty experiments, we realized the supply of saline or brine or liquid is not happening in perforated plate, just in perforated plate. And so then we designed those channels to supply water smoothly to the orifice from which air is moving upward in vertical direction. So it was a step-by-step process. Does that make you understand how the decision worked over there?
Yes, that helps a lot. Thank you.
And related questions, I'm happy to answer follow-up questions.
We were also wondering because your desalination machine is quite large and we wanted to build like a smaller contraption. So we were
Mhm.
wondering if you had any tips for like scaling it smaller, or like possibly simpler for like a smaller machine.
Yeah, definitely. Like, so when you scale it up or scale it down, the first question that we ask ourselves is, what is your target freshwater discharge rate? That is the first question. So you should start with that. Uh, Pick that. Based on that discharge rate, you can design rest of your components one by one. For example, in desalination, if you want to extract, let's say, 1 kilogram per hour of fresh water, then I will reverse engineer it, go back, okay. Then that means I need to condense that much water, fresh water, from that process because condensation is the last stage of the entire desalination. And how much can I condense over there? Okay, I can condense 1 kilogram per hour from there. Then how much heat I need to dissipate from it? I need how much heat transfer I need over there. Then I will design that heat exchanger. Okay, that heat exchanger that does not quickly fall, and at the same time, it gives you really good heat transfer that can ensure 1 kilogram per hour of condensate coming out of that heat exchanger. Then I go back. Okay, for that exchanger, what is going to be the inlet conditions? What is going to be the outlet conditions? That will help me design that heat exchanger and vary its effective as per my need. Beyond that, then I will see, okay, but this heat exchanger, so that it does not fall, I need to know specific constraints of the incoming flow, incoming steam flow. So that means, okay, I need this much. How can I achieve that? If I just evaporate and uh, if I just atomize and evaporate saline water, it will be a mixture of air, it will be a mixture of salt particles, it will be a mixture of steam. And I don't want salt particles in the heat exchanger. That means I need to have one another component before the heat exchanger that separates out the salt and let the air and steam go into the heat exchanger. Boom, that is salt over there. So things like that. We generally pick our deliverable, exactly what is our target matrix. Based on that, we keep on reverse engineering, reverse engineering, reverse engineering, and connected with the ultimate inlet that you're gonna get for your system, which is brine, which is the salt water. Does that does that help?
Yeah.
Yeah, that was very helpful.
Sweet, sweet. Okay, next question.
Our next question is that first of all, our contraption has like a bipartite system. So there's two parts. So the desalinization and there is also sanitation. So for our sanitation part of our system, we have like designed it so it is able to be solar powered. And we were wondering if there was like any way to power like this part of the system by like solar energy, or does it require too much energy to only be solar powered?
So when you say this part, you mean desalination or sanitization?
Desalination.
Desalination. Okay, that is a very good question. So how much? So my question is going to be, how much solar power is available in those areas, or how much is your reference to design a system? However, if we think about evaporative desalination, what happens is latent heat of vaporization for water is quite high, and that's why it requires so much heat. Um, so over there, if your solar radiation average is not sufficient, you might find it difficult over there. Like and designing something based off our work, our technology, it is going to require some good amount of energy, solar energy, thermal energy to evaporate all of that. But ultimately, it depends on how much discharge you are targeting. Basically, so knowing that, I think then I can answer more specifically, but it is possible. Let me say it this way. However, it is going to require so much of energy. So if you have plans and funding for that, then definitely pursue that. Otherwise, let me give you one new thought and one tangent to it. There are other solar desalination ways, and they are based on like entirely on solar energy, and they are more cost effective. And how they are is there was one paper that I studied 2 years ago, and it was they had a membrane and a floaty that was flowing on the water surface in a pond. And what it will do is it will trap the solar radiation, increase the localized temperature around that membrane, and that membrane if I'm using so many jargons, you can always ask questions when I answer. Okay. So what it does is localized increased temperature enhances evaporation, and then it condenses that water and collects salt on the membrane itself. Okay, so that is what its discharge rate. You cannot play too much around it. Ultimately, I'm going to say your discharge rate, your solar input is going to be one of the bottlenecks for achieving your discharge.
Thank you. That was very helpful. We'll definitely keep that in mind. And then going back to the fouling, when testing fouling, does the perforated plate atomizer ever decrease in efficiency over time? Or like have you noticed any like decrease in efficiency?
Okay, right. Good. Okay, then remind me if I sent you one paper or two paper. Okay, I sent you two papers. So if you go to WR Atomizer Deepak, which is the second file in it, if you go in that paper and go all the way to the last plot, let me give you the figure number. Come on, it's loading. Figure number 9. If you go over there, so figure 9 on WR, which is water research. It is published in Water Research Journal in 2022. So figure 9, what it shows that perforated plate atomizer, because its material was like it was 3D printed, so it was more porous and the surface was not super smooth. It had so many bumps and things over there. So that increased, like that facilitated little bit of fouling, but it was minimal. It was not really affecting the spray quality and everything, but it definitely like changed the cone angle a little bit. So on if we go on micro scale, then I would say yes, it might have affected a little bit of the performance. However, what I am going to suggest to you is very different from that. Do not go for perforated plate atomizer, but look at the bottom row of that figure 9. Can I share my screen really quick with you so that I can directly share it with you?
Yeah.
To share, okay. You will have to allow me to share. Or how about in chat if I just post that figure in chat really quick? Okay, matches. Can I? Awesome. So if you look at that figure in the chat, okay, great. Look at the bottom row. So what I did, this perforated plate atomizer enabled us to identify a new atomization mechanism itself. And if you adopt that mechanism rather than pivoting on the perforated plate atomizer, you can suppress fouling in even like commercially available atomizers. So that last row at the bottom shows that I picked a commercially available atomizer. I applied that atomization mechanism in that atomizer, and that suppressed fouling over 14 continuous hours. And salinity that I was using over here should be either 10% or 20% plus. I'll have to go check in that paper, but somewhere there, like definitely more than like 10% salinity. Salinity is pretty high. In ocean, in sea, you only see 3.5% salinity. So that is what I am going to suggest, that use a commercially available air blast atomizer and do not follow their guidelines. They will tell you, okay, supply air in these ports and supply water in these ports. However, as long as you have air jet surrounded by liquid, you are good. Your atomization is going to be better and it will never fall. It will never fall. Okay?
Okay, thank you so much. Um,
Totally.
with that, I just have like one like final wrapping up question.
Okay.
Just when we're speaking of like the quality, like the quantity of the water being dispensed, like how long would you say it takes to dispense say like 10, 20 liters of like desalinated clean water?
Hmm. So the system that we took a reference, our target was 10 kilogram per hour, and that means, and it was a pretty big system. So from thermal desalination, it will take like pretty good time. It's a long process. It's not like membrane. In membrane, it is easy. Like uh, you just pass through the pressurized water and have the membrane over there. But yeah, that is very fast. So it is gonna take time, but if you are targeting, and when I'm saying kilogram, you can directly convert it to liter. When I say 1 kilogram, that is also 1 liter for water. So 10 liter per kg we were targeting, and we were getting we attained that. Um, but that's lots of water. Okay. That's lots of water. If I am at your place, I will target like, I don't know what are the requirements of the competition, but if it is within those criterias, 1 kilogram or 1 liter per hour, it's pretty decent. Okay, it's pretty decent. Just imagine 24 liters per day, and then you have hundreds of those systems. Immediately, it is 2400 liters per day. So rather than making it a giant system, I will suggest make it a modular system. So every unit of your system will be just small for 1 liter per hour, and then you can have like 5 or 10 of those. It always makes the approach and the entire project simple. Does that help?
Yeah. Um,
Great.
thank you so much
Yeah.
for all of the questions that you answered, and we really appreciate like meeting with you and taking this time to like discuss our questions.
Thank you. Thank you.
Thank you
It's a
so much.
pleasure. Yeah, all the very best. And if you come up with more questions, you can always shoot me an email. And yeah, all the very best.
Thank you.
Thank you.
Take care. Bye.
Bye.
Bye.